So moving along, okay? So here is our thermodynamic definition of entropy. So this is our, for infinitesimally small changes, right? Our calculus-based definition. And of course, here is our definition for measurable changes. So when we can actually measure the change in the laboratory. So it says dq reversible. So the change in heat supplied reversibly divided by temperature by definition is ds. Okay? And that ds can become delta S by integrating over that expression. And of course, we recognize that entropy will be a state function. Heat is a path function. Okay? So what about entropy in the surroundings? Okay? So ds surroundings, and I could go on and I could expand on ds surroundings by putting dq surroundings reversible divided by the temperature surroundings. Okay? Well, as it turns out, in the surroundings, this isn't so important, whether it's supplied reversible or irreversible. And the reason for that is because the surroundings more often than not represent a gigantic reservoir of volume, temperature, work, heat, etc. Okay? The surroundings are almost always a humongous reservoir in comparison to the system. Okay? And so because of that, rarely does it matter if the surrounding entropy is brought about by reversible or irreversible change, as long as the second law is conserved. So what that means is when you're considering what's happening with the surroundings, whether it's reversible or irreversible, you still have to add that change to the change in the entropy of the system. And if that is a quantity greater than 0, then you know that entropy has increased. And you know that we can say that the system is being driven by an irreversible process, okay? The system. But all the same, if that process is to be spontaneous, it's the sum total of both the system and the surroundings that we have to consider, okay? And so we can simply write, by integrating along this thing, right? Integrate from initial to final, then we know the entropy of the surroundings is just the heat supplied to the surroundings divided by the temperature of the surroundings. And if we connect that even further, all right, we know that the change in heat of the surroundings is the opposite of the change in heat of the system. So for example, if it's exothermic as viewed by the system, then it's endothermic as viewed by the surroundings, or vice versa, right? So these are just connected by the opposite sign. And therefore, delta S of surroundings is going to be the negative Q of the system, still divided by the temperature of the surroundings, okay? So for example, if we want to think about like a bigger picture, like a bigger universal picture thing, okay? So if we think about heat being transferred to planet Earth from the sun, right? So we would have S total, okay? And so we can write the delta S of the system as just Q system divided by T system, all right? But then now that's going to be negative delta Q, So if we're now thinking of the surroundings, we could say that that's negative Q, I did that again. Negative Q system, that's what I'm trying to write. But now divided by T surroundings, okay? So these quantities will not be equal to 0 if the two temperatures are different, okay? And in the case of T surroundings being greater than T system, right? With, of course, that value of Q being the same. This is Q system, just one is negative, okay? This quantity will be much, much smaller, right? When the temperature of the surroundings is greater than the temperature of the system, we can say, we just proved that heat from the surroundings will spontaneously flow to the heat of the system, okay, when we have this situation, all right? And we can continue to play with these relationships in this way, right, to ask, is this process going to be spontaneous or is this process going to be non-spontaneous, okay? So this, with this in mind here, all right, and as a conclusion, S total is greater than 0. And that's specifically, again, for, I gave you that example of like energy being transferred from the earth, from the sun to the earth, but just, think of it as a more general example, right? Energy being transferred from a hot object to a cold object. If we define the hot object as the surroundings and the cold object as the system, we know this process will proceed spontaneously, okay? Moving forward, and again, that's just one example, all right? Okay, so, and then of course for units, right, we recognize that heat will have units of joules and temperature has units of Kelvin. So often we see entropy given in joules per Kelvin. Of course, we could, so that's for S. Of course, if we had molar entropy, joule per Kelvin per mole for the molar entropy. All right. Okay, moving right along. So now, taking advantage of that thermodynamic definition of entropy, let's come up with an expression for delta S of an ideal gas expanded isothermally in a reversible pathway. Right? So in other words, we have that definition, delta S equals I F dq reversible divided by T. And let's fill in stuff that we know. All right? Well, we know that isothermal, so anytime we see isothermal, what I want you to think of in your mind is delta T equals 0, which means delta U has to equal 0. Which also means negative Q equals W, because we know delta U is Q plus W. So for all isothermal processes, work and heat are equal and opposite. Okay? And so now what about the expansion? How do we deal with that? Well, we know work is negative PDV. Okay? And if we go and take that integral, right, and we plug in an actual equation, PV equals nRT, we know then that the reversible work supplied is negative nRT natural log of VF over VI. Okay? So resultingly, the Q supplied reversibly has to be positive nRT natural log VF over VI, right? And so therefore, we know now that we can say, if I plug this in, and I know delta S is going to be the integral, which we technically already integrated that work expression. So now, right, because integrating dq just gives us, so from final to initial, right, just gives us Q reversible over T. Well, we integrated that already. We integrated it from V initial to V final to get the work, all right? And so the delta S then is just going to be Q divided by T. So that just results, so let's write that down. Q, oh, I did right there. Q reversible divided by T, okay? So now that just equals NR times natural log of VF over VI, okay? And so thus we can see here, we know R has units, so this would be the 8.314 joule per mole K, right? So when we multiply this by the total number of moles, we will have our total entropy. We'll have entropy in terms of joules per Kelvin. All right? So let's see here. Moving right along. So for adiabatic processes, so this is another scenario we talked about, right? We know in an adiabatic process, dq equals 0, so there's no transfer of heat. So then we can also say that q surroundings equals 0. There's been no heat given, which means the delta S of the surroundings would also have to be equal to 0. Okay? And so therefore, S total is only going to be dependent upon the entropy of the system for an adiabatic process. And of course, if this is greater than 0, then it's spontaneous. Okay? And we have to be careful. Not every single process is spontaneous, right? So we can't just go and say that every single thing we can think of is spontaneous. But if we were to say we have an adiabatic process that proceeds spontaneously, then we know that that has to be driven entirely by the entropy changes in the system. Okay?